All right, guys and gals, today we're going to continue on with right triangles, and ironically, we're going to kind of take a step back from that. So far, all of our work in trig has dealt solely with right triangles. So the question now is, well, what about the non-right triangles? How can we work with those? And believe it or not, trig will work with those with some minor tweaks. What we're going to look at today is called the law of sines, and what it is it's a way for us to work with non-right triangles while still using trig. All right, so let's take a look at it. Yeah, maybe. There we go. So take a look. Here is the law of sines. So for example, if we've got a triangle, any triangle will work, but specifically we'll use it with non-right triangles, though it would work with a right triangle as well. Any triangle that will work. If we've got A, B, C as sides opposite their angles with the same name, then what it allows us to do is to create this ratio where the sine of angle A over side A, that ratio is equivalent to sine of angle B over side B, as well as the sine of angle C over side C. So it creates this proportion. In other words, regardless of the triangle we have, so long as we know certain things. So for example, if I know two angles and a side, or if I know two sides and an angle, then in theory, we should be able to work out that missing angle or that missing side and continue to work our way around the triangle and be able to solve it. In other words, to find all the sides and all the angles. So let's take a look at it and try it. So here's our first example. We're going to find side B, and we're asked to round it to the nearest tenth. So when we use the law of sines, it's just a ratio. So for example, let's start with angle A. So I'm going to do sine of angle A, and in this case, angle A is 37 degrees. Let's write that down, 37 degrees. And then that's over side A, in other words, the side opposite it. So in this case, 3. Right? I've got angle B here, so it's 68, so sine of 68 degrees, and that is opposite side B. Right? So in other words, we're going to take this proportion and solve it. So I'm going to do some quick cross products here. So B multiplied by the sine of 37 is equal to 3 multiplied by the sine of 68. And notice I'm not actually doing the work yet, right? I'm not going to figure out what sine of 68 times 3 is just yet, right? We're going to work algebraically until the bitter end. That way we don't round anything. Right? So the next thing I need to do is I need to get rid of the sine 37 over here. So we'll divide it on both sides. So side B is equal to 3 multiplied by sine 68 over the sine of 37. So if we wanted an exact answer, well, then that would work, obviously. In this case, they're asking us to round, so let's go ahead and do what we're asked. Remember, with our calculators, all right, real quick point of order, make sure you go to mode and double check and make sure that you are in degrees as opposed to radians. If your calculator for some reason switches back over, whether you reset it or you're using a program or something, just make sure it's in degrees. Otherwise, you'll be wrong because we're measuring everything in degrees, not radians. So when you type this in, here's what I would do. I would do 3 sine of 68. Again, close those parentheses, get in the habit of that. In this case, we can go immediately into divide sine 37. So sine of 37, again, get in that habit of closing the parentheses. Notice here, if we didn't close that parentheses, we would be doing 68 divided by sine of 37 within that sine situation. We don't want to do that. Cool. So in this case, finding B, we're rounding to the nearest tenth. In this case, we're finding B to be approximately 4.6 units, whatever that is. So B is approximately 4.6 units, whatever it is, inches, miles, we don't really care. So that's how it works. Notice we have to have angles opposite sides, so angle opposite side, in order for this to work. All right, let's try another one. Sometimes we'll just be given measurements. So in this case, we've got triangle XYZ. Now, if you don't have an actual triangle, one thing you can do is just sort of draw yourself a nice nondescript triangle. All right, and it doesn't matter that the angles and sides aren't to scale. Again, this is just a rough sketch. So I've got X, Y, and I've got Z. All right, so let's start putting in the coordinates that we're asked, or not coordinates, the measurements that we're given. We're asked to find Z, so I'm just going to underline that just to remind myself that's what I'm looking for. Let's see here. We know that Y, so the side opposite angle Y, is 17 units. right? We know Z, the side opposite angle Z, is 14 units, and that angle Y is 92 units. All right? So notice we are set up to be able to use the law of sines. Notice we've got the angle opposite the side, missing angle opposite the side. We're all golden. So let's set it up. So I'm going to say the sine of angle Z, so I'm just going to put a Z in there for now, over 14 is equal to the sine of 92 over 17. And again, I'm not going to do any actual work until the very end because I don't want to round anything. So the first thing I'm going to do is I realize I've got this sine of Z. Z is what we're looking for. I need to get rid of that 14. So the first thing I'm going to do is multiply both sides by 14. So I have sine of Z is equal to 14 sine of 92 over 17. Excellent. The next thing we're going to do is we got to get rid of the sine. So remember, to do that, we'll use the inverse of sine. So angle Z, all right, or if you wanted to, you could write the measure of angle Z, if that makes you feel better, is equal to the inverse sine of all of this. So 14 sine of 92 over 17. So let's talk about how to enter that into our calculator in a way that's not going to be overly cumbersome and in a way that we can get consistent answers each time. So what I'm going to do is I'm going to ignore this inverse sine for just a moment and focus on the inside. So I'm going to do 14 sine of 92. Make sure you close those parentheses, get in that habit, divided by 17. Go ahead and hit enter. And then I'm going to immediately hit second, our inverse sine, and then second, and then the button we'll hit kind of off screen there is down here. Your negative sign, rather, is answer. So what that's going to do is that's going to take the previous answer and just put it right in there. Cool. And in this case, we're asked to round to the nearest whole degree. Cool. So in this case, about 55 degrees. So let's write that in. So the measure of angle Z is approximately 55 degrees. Right? Excellent. Law of sine. Pretty simple, pretty straightforward, not a big deal, just working with proportions. Right? So let's look at a proof of it. Now let's talk about why this thing actually works. Right? So here's our proof for the law of sines. So notice what I've done is I've drawn once again that nice nondescript triangle, ABC in this case. I've also added height h. So I just took it from C down, let that intersection point be D. And remember, heights are altitudes, it's another name for it, and we've got that nice right angle drawn in. Notice, now that we have right triangles, we can do some things. Let's take a look. First thing I'm going to do is my given statement. So in this case, I've got triangle ABC with height h, so there it is. The next thing I'm going to say is that the sine of angle A is equal to h over b. Notice that's a right triangle here. We can draw that in. And then we've also got the sine of b equaling h over a. And the reason that we can give for that is simply the definition. There we go. I can't spell. Definition of sine. Right? That's what sine is. Right? It allows us to say that. All right. The next step, notice down here, I'm going to multiply by b on both sides, and then I'm going to multiply by a on both sides. So this is simply a multiplication property. Slash substitution. Notice we've done that multiplication and done the substitution all in one step. Awesome. So now notice I've rewritten these two sine issues to be equal to h. Since they're both equal to h, that means they're equal to each other by yet again another substitution step. Right? And then from there, we can simply rewrite it with a little bit of division. I can divide both sides by b, divide both sides by a, and then substitute. So the division property, again, division property of equality with a combination of substitution. And there it is. Now notice, that proves it for a and b, angles and sides respectively. We could do a similar process with C. We could simply draw in a new height and do the same process all over again. But that gives us proof for why this works. It's based on every time we have an altitude, we can generate these right triangles, and it'll work for any triangle that we've got. So moving on. Let's talk about solving triangles. This is where we need to find all angles and all sides. So again, we've got a nice nondescript triangle here. We're asked to solve ABC, and by solve it means find all side lengths and all angle measures. So let's take what we know, we'll write it in, and then we can start finding what we're missing. So angle A is 33 degrees. Angle B is 47 degrees. Side B up here is 14 units, whatever that is. And then we're going to take all of that and work through it. Now, notice we've already got two of our angles, right? We've got 33 and 47. So I don't need to do any sort of trig for that. I can simply add those together. We get 80 and then subtract that from 180. So we know this angle here, angle C, has to be 100. So always look for the shortcuts, folks. We don't have to use any fancy trig work, whether it be law of sines or anything else to get this. Just use what we know about triangles. In this case, we can use our angle sum theorem. So now that we've got that, we're set up to do pretty much whatever it is that we want to do. So for example, I could set up sine of angle A, so in this case 33 degrees, over A, I don't know that. And then I could set it up as sine of 47 degrees for angle B over 14. All right. And then we'll just work from there. So we'll multiply both sides by A. So we'll get A sine of 47 is equal, multiplied by 14 on both sides, 14 sine of 33. And then we can divide both sides by sine 47. So A is going to be equal to 14 sine 33 over sine 47. All right. And that'll give us that side exactly. So let's go ahead and work that out. And we were asked to round side measures to the nearest tenth. Okay, so again, typing that in, making sure that we have everything. So 14 sine 33, close parentheses, again, get in that habit, divided by sine, where's my sine button? There it is, of 47, close parentheses, hit enter. So about 10.4. All right, so let's write that in. So we've got about 10.4. Now, that is a rounded number. Okay, so when I find C, I am not going to use this number. I'm going to keep using 47 and 14 because those were exact numbers that were given to me. All right, so always try to use exact numbers if possible. So once again, I'm going to use sine of 47 over 14. Those were given to me and they're exact. I am not going to use this 10.4. It's going to give me a rounded answer here, which leads to even a further rounded answer here. All right, we've got sine of 100 over C. And then we'll basically just repeat the process, right? We'll do everything all over again with a new set of numbers. So we've got C sine 47 is equal to 14 sine 100. Divide by sine 47 on both sides. So C is equal to 14 sine 100 over sine of 47. And again, we'll just simply enter that into our calculator, get our approximate answer, and move on with life. So 14 sine 100, close parentheses, get in that habit, divided by sine of 47, close parentheses, and we're getting an answer of roughly rounding to the tenths position, so 18.9. So 18 and 9/10 for side C. And there we are. So that's how we solve triangles. Take what you know and then work through your law of sines to get what you need. All right? Fairly straightforward, to the point. Now, let's talk about a real world situation. All right, I like this problem because you'll see it a lot of times in like SAT, ACT. They love problems like this. So take a look. When the angle of elevation to the sun is 62 degrees. So in other words, if you were standing here and lined up your line of sight with the end of the telephone pole and the sun, we get 62 degrees. Right? And it is tilted at an angle of 7 from the vertical. So in other words, if the telephone pole was straight up and down, it would be here on this black line. Unfortunately, it's tilted maybe. So maybe they had a windstorm and it pushed it over. So this angle right here with the pole and this straight up and down is 7 degrees. So this 7 is not up here. This 7 is not over here. 7 is here. The difference from vertical to what the pole actually is. All right. And it casts a shadow that's 30 feet long, find the length of the telephone pole to the nearest tenth of a foot. All right, so let's do that. So obviously we've got 62 degrees here. We need to find this angle here. All right, that's going to be very, very helpful. So if I've got 90 degrees, if it's straight up and down, less the 7 that it's leaning, we're looking at an 83 degree angle here. All right, so that way we've got that angle in there. So notice I've got a 30-foot shadow across from an angle I'm still not sure about, and then a 62 across from the pole. So I need this other angle. So if I take 62 and what did we say? It was 83. All right, that gives us 145. Subtract that from 180. We get a difference here, and we'll make it 3 marks here for this, of 35. All right, so let's set up our law of sine. So we could say the sine of this 35 degree angle that we just found across from that 30-foot shadow, all right, is going to be equal to, so I need to know the pole distance. It's opposite the 62 degree angle. So sine of 62 degrees over that pole distance, we'll call it x. All right? So there we are. We've used our law of sine. Get that camera to refocus. We've used our law of sine to be able to figure out that distance. So again, we'll cross products and we're off to the races. So x multiplied by sine 35 is equal to 30 multiplied by sine of 62. We'll divide sine of 35 from both sides. So x, our pole length there, is 30 multiplied by sine of 62 over sine of 35. And again, with a calculator, we can do this relatively quickly. We'll get 30 multiplied by sine of 62. Again, get in that habit. Close those. Oh, not cosine. Look at me. Sine. There we go. Sine of 62. And again, make sure you close those parentheses. Divided by sine of 35. Again, close those parentheses. Get in the habit now. And we get a distance here rounding to the nearest tenth of a foot. Our distance x is approximately 46.2 feet. And in this case, since we know what the unit of measure is, we'll go ahead and include it. We won't say units. It's not some random number that we were given. We know that it's in feet. Right? So again, that's how that will work. So again, make sure you mark your diagrams up. That's the one thing that I would say. And if you're not given a diagram, draw one yourself. It makes this work a lot easier. All right, so far everything's been pretty easy, right? Not a big deal. It's just a proportion. All right, I'm about to throw a wrench in the works. Take a look. Here's when you can use the law of sines, right? There's 2 cases where law of sines is allowed to be used, all right? The first case is you know the measures of 2 angles and then any side of that triangle. So in other words, you've got an AAS situation or an ASA situation, all right? And that gives you, because again, with 2 angles, you can find that third in case it's not the one that you need. So this case, I'm going to call it the easy case. All right, it's just a matter of using it and moving on. The second case, you know the measures of 2 sides and an angle opposite one of the sides. In other words, you've got an SSA scenario. This is where things can be tricky. All right, and we call that situation the ambiguous case. Ambiguous meaning we're not certain of it. We call it the ambiguous case of the law of sines. Anytime you have an SSA situation. So let me show you. Version 1. Here's my triangle. All right, I'm going to bold it in a little bit here just to make it a little easier to see. Notice that BD, this distance, and notice we've made a circle here, and we'll talk about that circle in just a minute. But BD is not only the side length, it's also the radius of this circle, and it is 3.5. So let's write that in, 3.5. All right. We know that AB, so this distance here, is 5.79 centimeters. And that we know that BAC, so this angle here, is roughly 29.26 degrees. Cool. If I asked you to solve this triangle, we need to find 2 more angles. So we need to find angle B here, so to speak, and angle D here, so to speak. And if we do the math, we could find that those angles are 97 and change and 53 and change, and that AD, this other side length, is 7.15, almost 7.2 centimeters. And you would think, okay, so what? Who cares? But I want you to notice something. Here's version 2. Pay very close attention. Here's the triangle that we're working with. Now remember, the only thing we knew about the triangle going into all of this is what BD was worth. That's where the circle comes in. Notice this is where our original BD was. All I've done is simply shifted it over. And because it's a radius of a circle, it stays the same. So this is also 3.5 centimeters. Notice that AB didn't change, so it's 5.79 still. And notice because I shifted side BD, it never affected angle A. So this is 29.26. So let that sink in. Two exceedingly different triangles, side, side angle, side, side angle, and notice all of those measurements are the same. But notice they relate to two completely different triangles. Oh no. So what do we do? All right, how do we deal with that? Well, let me be clear with you that the math, all right, isn't wrong. All right, law of sine works. The issue is here. All right, your calculator is going to assume this version. Okay, it's always going to assume version 1. And let's take a look at angle D in particular, all right? Because notice, the way this is set up, I would have to solve for angle D first. Notice I don't have enough information to solve for B. So angle D, in this case, is our issue. Notice your calculator, if we worked this out, would get you roughly 53 degrees, all right? Almost close to 53 and a half. That's what it would produce. However, notice we said there is a second version of the triangle that could work. In that version, angle ADB, in other words, angle D, so right here, could also be 125.82 degrees. So I want to try something here. Take a look. If I take the 53.48 and add it to the 125.82, watch what happens. We get a number that's almost how much, right? We're almost at 180 degrees. Now, the reason we're off is because, well, these are rounded numbers. But here's the deal. The two versions that we get, okay, are supplements. Meaning that when I solve for version 1, and if I know I'm dealing with an SSA scenario, okay, then I'm going to have to solve it once with this version. So once I get that number, I keep working out to find B, find AD, and finish up. Then I'm going to have to stop, take the supplement, draw a new triangle with that new measurement in, and solve it a second time. So in other words, if you find an ambiguous case, you need to solve for version 1, all right, and your calculator will automatically solve for version 1. Okay, it'll assume that that is a acute angle. Once you're done with that, find the supplement. Okay, and that's going to be you. Okay, you are going to have to find that supplement. Okay, once you've got that supplement, find version 2. Okay, so your calculator will automatically do this. All right, once you realize you've got a side-side angle situation, redraw it, use that supplement, and then solve again. Because notice, angle B gets changed, angle A or side AD also changes. But here's the deal. Question always becomes, well, which version is correct? All right, well, it depends. It's kind of like a quadratic. When we solve quadratics, we get two answers sometimes. However, in the real world, both answers may not work. For example, let's say this was a fenced-in area and we only have so much fencing to use. Well, notice that this version of the triangle is going to have a longer perimeter than this version of the triangle, much shorter perimeter. So if we're dealing with, say, a perimeter scenario and we've only got so much fencing, well, maybe this is the version that we really want. All right, as opposed to this one, which would be longer. So we're going to have to pay attention to our real world situations to know which version works. And shoot, both versions in theory could work. If we're dealing with just a random triangle like this is, it's really not related to the real world, then we would need to provide both. Here's one particular version that could work. Here's another version that also works. So again, real world, odds are only one of them is going to work, though both could. If we're talking about just general cases, then you'll need to provide both. And in class today, we'll talk more about that. How do we deal with these situations? How do we spot them? And then how do we write our answers to show both, right? If you have any questions or concerns, please let me know. Have a good day, folks.